use something other than standard in and standard out as your two ends of the pipe here. Yes. Anyway, all right. So netcat will do the same thing here. Okay. Anyway, so you can send stuff back and forth, and it will happily sit here and wait. All right, so in terms of use of, for this particular class, let's go ahead and close that one down. What if I connect to a different port? Software.lcc.edu. All right, so port 80 is the web server. All right, there's port 80. We're connected. Now that we're on the web server port, the thing about HTTP, one reason to use this one as a demo is HTTP, Hypertext Transfer Protocol, the thing you have at the beginning of your web address, is a text-based protocol. So if we can speak web server here, we can talk to it. Hey, there we go. Oh. All right, we didn't speak very good web server here. Good HTTP. Sorry. All right. So we got an HTTP 1.1 bad. We got a bad request basically. It's like we didn't understand. All right. I'm laughing because we're disconnected. Well, I think that might be because we'd already sent one in there that was bad. I think we might have already been. Say if we say hi there, we also get bad requests. And then if we say anything here, we're going to end up back there. All right. You can look up HTTP. It's not that complicated a protocol. But you can go ahead and connect to a server and start talking to it there. Oh, let's have a talk with the SSH server. All right, the SSH server automatically sends out this little tag that identifies it. That'll be real handy if you're looking for SSH servers on a machine. You can go ahead and connect to each port, and if they send back this, then it's an SSH server. A little harder to tell a web server, it doesn't send anything, but I guess if you start talking to it, it'll send you a bad request. So you can figure that out too. All right, hi. Protocol mismatch. Yeah, we said something outside the protocol. SSH is a binary protocol. It doesn't necessarily have everything in ASCII text. So because of that, we're going to have a lot of trouble trying to speak SSH through ASCII right here. Not necessarily impossible. Usually terminals have a way to enter special characters. So if we can enter special characters, we can pick ASCII characters and special characters that have the right values, and maybe a hassle. All right. Yes, you can connect to different ones. Let's connect to the port 5190. All right. You see a few things here that didn't match in a terminal. That's because this is also a binary protocol that this server here is running. But that said, this server did send an ASCII text description of something, which comes out as ASCII text. So if you have a binary protocol and something is an ASCII text, you'll see it on netcat. Same as if you were to cat a program. Say you compile a program and cat it. If you've got a string inside the program, you'll actually see that when you print it out. All right. Yes, different ports, different responses. So that's how you can use it to connect to things. You can also use it to start a server with -L and -P, like I showed you. All right, let's do NC-L-P 5100 again, and let's go talk to it with a web browser. All right, so I have one open. Port 80, no, it's not 80, 5100. All right, so we connect our web browser by software port 5100. First of all, it's waiting. Down here, so there's the request the web browser sent. So you can see it said a little bit more than get slash. Maybe if we tagged it with HTTP/1.1, it would have worked, or maybe it would have required a little bit more. All right, so down here, we have the opportunity to play the server's part of the conversation with the web browser. Hey, look at that. Web browser actually showed it. Web browsers are fairly accepting of things that don't quite fit into the protocol. It's actually kind of irritating if I try to use HTML as an example of a computer programming language or anything like that, because when you make a mistake, the web browser ignores it instead of telling you there's a syntax error. Anyway, so there we go. We said hi, and the web browser actually rendered it for us. Cool. All right, so you can play either role as client or server with NC. So I went ahead and put these two examples here, how you do both sides of the conversation, and so now you know how to use it. Okay, one other note. I think I said briefly that I have to run the server on Isoptera. Yeah, if I say MCLP and say 5100 on here. So I just opened up port 5100 on this machine in this room. So if I go over here and I say, okay, what's the IP address? The IP address of this machine in this room is 192.168.18.25. This is a local address, and I don't think Isoptera is going to find it. 192.168.18.25 and port. All right. Yeah, it's just going to sit there. Oh no, it found it. All right. I was thinking I wouldn't, but it did. All right. So here's what I did. Isoptera. So the network configuration here is a little bit more complicated than I've been letting on, so I guess I might have to explain a little bit to make this make any sense. Let me first go ahead and show you a place that definitely does not work. I'm going to go home. All right. This canary. Okay, I'll go ahead and run that again. And down here, we'll go ahead and run the exact same command that worked on Isoptera. And if I say hi here, you can see, nothing. That hi is the hi I typed it here. All right, so it totally does not work. All right, so let's back out and explain the network configuration slightly. All right, so Isoptera is actually pretty close to us in the network sense. Our lab over here has, maybe I should start with some history. All right, so here at MLH 310, we used to be a part of the college network when I first got here, and we had a switch up in the up there that was 100 megabit. So after it didn't even take a couple of years. After not very long here, I got this grant and had some money finally. So I asked IT if they could use the grant money to buy us a new switch, which they did. So it's about a $3,000 switch up there. All right. So then after that, we had gigabit inside this room. But it turned out that we actually didn't have a very fast connection to the rest of campus. So I talked to IT about it, and they thought it sounded like a good problem to fix. But before they did that, before they got it completely set up, we were just talking about it, we had a little incident. Jesse was re-imaging the machines in here, and when he does that, he sets up a DHCP server, Dynamic Host Configuration Protocol. And what Dynamic Host Configuration Protocol is used for is when you turn on a machine, it can go ahead and ask, I'm new here, what address should I be using? Where is the router? Where is the DNS server? Where is the bathroom? It can get itself oriented. So he set one up. All right, so IT also has a DHCP server. Well, normally our DHCP server only served this room, but he made a little error somewhere, and I'm not even sure where, and he's not even sure where, but somehow we managed to become the DHCP server that was serving up addresses to the rest of the building. So any computer that was turned on failed to work because it instead configured itself up to be part of our imaging up here. Anyway, so we talked to IT about it, and they're very understanding folks there. They were like, well, maybe we should exile you all to Siberia. And so that's what they did in a network sense. We've got our own network on this side. And it's very nice, actually. They suggested that, and we're like, yeah, let's do that. So we've got essentially our own network that leads to our own port of the router off to the outside. And so actually a lot of stuff will work here that won't necessarily work on the rest of campus, connecting to particular ports and things like that. All right, so as part of that, I'm not quite prepared to explain level 3 switches in this class yet. All right, so they've got switches configured to make all of this stuff happen. If you're a ISADI, you know how it works. If not, we'll get there. All right. So Isoptera is on our side of the network, not the IT side of the network. And so I didn't realize that it actually knew where 192.168.18 was. But in a network sense, it's actually very close to us, and evidently it does actually know where we are. The thing I was talking about was configuring the router, the switches. So fancy switches offer the chance to configure and basically agree that some part of the network should look like it's all on the same switch, even though it's not. So they actually use higher levels in the stack to make it look an awful lot like the network is configured very differently than it's actually configured. All right, so what it comes down to here is this room, one port in my office, but not the other one port in Charles' office, but I think he's got another one down there somewhere else, and I think maybe one in Nina's. I can't remember if she has one or not. Or actually appear to be on the same local network as here, like we were plugged directly into the switch. And in Isoptera is, I thought it was in a little bit more removed, but I guess it's not. And so then Isoptera can go connect to the internet. Now, for the internet, you definitely can connect to a 192.168.18 network. The 192.168 and the 10 dot and one in the B range. I think it's like 172 or something. I always kind of forget. Somebody here probably remembers. Anyway, they're all local networks, and so you don't have an internet address ever that starts with 192.168. All right, so back to using Netcat and hosting servers. If you're like, I want to start this server, and this is going to be the server that serves up this important thing for the entire world, and the server's address is 192.168. All right, you got a problem. You can stop right there. Your server is not going to serve the web page up to the entire world. So you have to find something that has an internet-facing IP address. And so that's why I kind of habitually, even though I guess I didn't need to in this particular case, start the servers on Isoptera. If we look at Isoptera's, I have pretty big IP address for 74.118.22.194. This is the kind of address where if you put it into whois, it will actually go and find it for you as an actual, internet-facing IP. All right, there's that thing for that there. All right. Okay, there's who we are. It's Idaho Regional Optical Network, which conveniently makes IRON as the acronym there, which I always find a little funny because iron conducts electricity, but you can't actually put any light through it, and this is an optical network. But anyway, IRON for Idaho is what it is. All right, there we go. Okay, so that's the note about that. So let's start talking about network programming some more here. I put that interlude in there because occasionally I'll notice somebody trying to start the server 192.168 and they're like, what is wrong with my network program? I looked through this 10 times and then I compiled the example from class and it still doesn't work. Well, could be that. All right. Yes, stuff we'll need to learn. Addresses and how to deal with them. So the addresses, they will end up being more complicated than it seems like they should be, at least in C. They're about as complicated as they seem like they should be in Python. Sending stuff through a socket, so we'll have to open up a socket. Socket will make a whole lot more sense once you see one. And then we'll have to deal with multi-threading. So a lot of times the server supports more than one client. Typically, if you connect to World of Warcraft, you do not expect exclusive use of the server. And you might not want exclusive use of the server because if you're going to go on a raid with other people, it would be nice if they could actually join too. All right, so a very traditional way, and it's not the only way, but it works fairly well, to deal with multiple clients is to start a thread for each client. And then for each client, you've got one thread maintaining communication with them. So I'll talk about multi-threading a fair bit to make that work. The alternative is to have a single thread or a thread pool and check and see if a client has something to say, and then move on to the next one and see if they have something to say, and so on. And you can run those and do that, and that can actually work too. All right, user interface for network applications. So the difficult thing on the network applications is you can't just write a simple command line program and have it work nicely. So if we set up our little Netcat chat server again here, and all right, this actually works, so why not? All right, so let's say something here. Hi. Now here we start preparing a very witty response. I'm tired this morning. But meanwhile, this person is busy saying something. Hi. You see it appears right in the middle. It's not very nice in the user interface sense. and this person's trying to say something interesting. But you have to be quick if you want to say your whole interesting thought before somebody else says anything. Now, if you've got nerves of steel, all right. Look at that, it worked. I mean, I have my typo on the key there. But despite this, it actually worked. If you can just kind of ignore this and keep on typing your thought you meant to type, it will actually work. All right. Anyway, but the user interface there is not necessarily very good. So for a network application, you typically have to be able to display something at the same time you're ready to receive input. So this involves splitting the screen in some way and doing some kind of windowing approach. That doesn't necessarily mean it has to be outside the terminal. There's a library called Curses that will allow you to do kind of GUI type stuff in the terminal. At some point, I'll show you a few different Curses programs I've wrote. I don't necessarily recommend it for this class, although it can certainly work. A lot of times people just end up cursing it after a week or two. It's a little bit convoluted. But that said, quite a few people have done network clients for this class using Curses, and it works fine. I suspect that most of you would be happier using some kind of GUI library. And so we'll talk a little bit about GUI libraries. It's kind of a weakness actually in our curriculum that at some point we probably ought to fix. There isn't actually any spot in our curriculum where you learn to program graphical stuff. It happens a lot of times, like in CS-435 or something, you'll end up doing it. And I guess in this class you will. But there's not like, when I was taking, I was an undergraduate, we had CS-351, Windows GUI programming. And it was required for a while, and then it became a non-required class because a lot of times you just end up programming servers or apps or something when you program, not necessarily Windows GUI. So it became an optional part of the curriculum. But the class was always there. If you wanted to learn how to program a GUI, you do that. And when I took it, we were using Win32. But after that, there was MFC, and then the whole .NET, and there was WPF/E, which I'm not sure anybody actually uses. And so it was I guess it's a little obsolete now. But generally speaking, the GUI systems have a fairly common way they go about stuff. You'll have buttons and text boxes and things, and then you'll have callbacks. You click the button. If they click this button, and you run this function. General structure for them. In some cases, they're a little bit more convoluted. Let me say convoluted. In some cases, they're a little more flexible. Flexible and convoluted go hand in hand with stuff. Sometimes it just depends on your mood that day, whether it's convoluted or flexible. Anyway, QT, for example, is a setup of slots and signals. So a button produces a signal. The signal can be wired to a slot. The slot can have a function associated with it that it runs, and that allows you to make some kind of, hooking up of buttons and controls to functions. So sometimes there's something a little bit more elaborate, but generally speaking, you just go through and if they click on this, do this, and if they enter text in this one, then let's just ignore it. But when they click on this one, we'll grab the contents of that box, stuff like that. I'll show you with some library or other. We'll just have a quick go through on it. It's not that complicated to just start making a little GUI that'll work fine for your network program. But the more elaborate your GUI gets, the more complicated it is. And then you end up with little issues where, when I slide my sliding menu over, it actually obscures this information that they might want to actually see when they're entering the menu, so we need to rearrange this stuff. It's one of those things where it's easy to do it, but it's hard to do it well. It's like playing the piano, you could probably walk up and play a song within, 10 minutes, but playing it well requires a lot of practice and work. All right. Disconnecting. Disconnecting is a weirdly complicated problem because a lot of times it can cause a problem for your server if one of the clients just somehow unexpectedly disappears. I think I mentioned that before with Jesse's test script, where if you pack like 1,000 bots into a room in the game, and then you put in a new bot, they'll be sent all the information, but you just go in a room and immediately disconnect. So the server's busy trying to send all this information to a connection that's now been lost, and in some cases you can even crash the server. there is a signal that gets sent when you try to send to a disconnected socket. And so if you handle that and figure out which client has disconnected and stopped sending them things, that can work. But if you've got a multi-threaded program and one thread is stopped and it's dealing with that, but some other thread is busy sending, you can end up with a little more pervasive crash bug sometimes. All right, anyway, not too bad though, we'll figure it out. All right, so first piece. So we looked at the simple server last time. Let's go ahead and open that one back up again. Go ahead and, I think I just showed it to you on Nimrod last time. I have it in here. All right, I got a simple server and a simple client. I'm going to go ahead and just copy both of these to server, the current examples. All right, and we'll go ahead and let's take the software and modify it. No, that's odd. I thought I was pretty certain I just copied it.
You put that at 430.
You're right, I did. I thought I was silly. Alright. Oh, because I didn't bother to navigate the right spot. Okay. One of those mornings when my brain is left me. Alright. There we go. I guess I could have also just moved them over from CS-435. All right, anyway. So, simple server. All right. Last time we ran this and it worked, but I just kind of went through this real quick. Didn't bother to explain very much because we were pretty much out of time the entire time. All right, so for C programs, they just kind of start like this. The arguments there, we can pass arguments to this. It doesn't actually use either argument. It might be nice if it did, so we can specify which port the server runs on, for example, which is right here. But that's not what we're doing. All right, so this sock adder in and sock adder addresses and sockets. So let's start with what a sock adder in is. That should work. All right. I want to be able to switch between 2D. All right. You notice no manual entry for it. Interesting. So a lot of times when you're looking at a manual for these things, you have to go and you find the function or use for, and from there you can often find it. So the sock adder in is eventually used at this bind function right there. All right, that's how I find that. All right, so here's bind, and so you see we're using the sock adder in. And so bind takes a sock adder in. So that's what we're busy making for it. All right. There, that switches back to port correctly. All right. So that's the third parameter there. So we're looking at what bind needs to know. It's got to know the port and the address and the address family, like what type of address it is. But you notice we made a sock adder in, and over here it says construct sock adder, no underscore in. All right. So it mentions down here, the actual structure path for the ADDR argument will depend on the address family. The sock adder structure is defined as something like, and so there's a sock adder, and so it's got this SA family type. SA family, that would be our sock adder family or address family. And then we've got some data, 14 bytes of it right there, which is enough for our INET address. Okay, so the only purpose of the structure is to cast the structure pointer past an ADDR in order to avoid compiler warnings. See example below. Example. All right, here's an example. There's the call to bind right there. And you can see they've taken this my adder, that's the address they're at, and cast it as a struct sock adder star, a pointer to a struct sock adder. All right, so my adder is up here, and they've got a struct sock adder right there. I think that's for a Unix socket, and so that's the my adder there, and then they're going to set up the address right there. So the address family is AF Unix, and then they're copying the path over to it. All right, so that's a different address family than we used. And so this sock adder here can be from a variety of different address families. Now this next thing right here explains how much space the address takes up. Since we can be sending in a variety of different addresses, they might take up different amounts of space. If we use an IPv6 address, an IPv6 address is 128 bytes instead of 32 like an IPv4 address, then it's going to be bigger. It's not just 32 with our IPv4, we've also got a port associated with it and an address family, and so the struct sock adder is bigger than 32 bytes. Bits, excuse me. It's not bigger than 32 bytes, that'd be pretty big. All right, so that's what we're making. So you might say, how are you supposed to know how to make a sock adder in? I mean, this page doesn't tell you. All right, if you look for, not that one, manual section 7 has a lot of kind of deeper explanations. And so actually, I think this was mentioned in the bind page. Let me see. Bind. All right. The rules used in name binding vary between address families. Consult the manual entries in section 7 for detailed information. For AF INET, that's the one we're using, see IP section 7. For AF INET 6, that would be IPv6, you're going to see IPv6 section 7. All right, so each of these ones has a page in manual section 7. All right. So we look over here in manual section 7 at IP, we find a bunch of information on the Linux IP version 4 protocol implementation. Okay, there's includes that you typically use when using IPv4, and yes, you create an IP socket using socket. There's how you do that. We'll get there eventually. But then finally down here we have address format. All right, here is what a sock adder in structure is. Now we can find it. So we need to set the family to AF INET. We need to have a port. That's the port in network byte order. This is big Indian. Our machine there is little Indian. We'll have to convert it. And then we have the actual address. That's a struct in adder. Struct in adder. And the struct in adder has a uint32t, unsigned 32-bit integer. That's our actual address in network byte order. All right. Why has it got a substructure right there? Well, it does. All right. I don't have a super good explanation for that one. Sorry. Okay. The probable explanation, and I don't know if this is even right. Some of the address families work differently, and so if you just have a structure that represents your address on all of them, then you can kind of have a consistent 1, 2, 3 kind of structure here. But that's speculation. All right, so there we go. That's the address and address family. So if we go back over to our program here, we set the 3 members of the address structure here, and so now we have a complete sock adder in, which we can pass to bind right there. All right, I didn't really talk much about what bind does. Talk about bind. All right, I realize that probably for a lot of you, the first thing that comes to mind when you hear bind is like a bind wound power or something in a game that increases healing rate. But that's not this. All right, so when a socket is created with bind, it exists in a namespace, address family, that has no address assigned to it. They're talking about the socket call on this line right here. We're making a socket. It is an IP version 4 socket, and it is a stream socket. That will be TCP. We don't need the last parameter for this one. All right, so once we've got it, there's no address assigned to it. Bind assigns the address specified by ADDR, that's that address right there, to the socket referred to by the file descriptor sockfd. That's the one we made using the call to socket. All right, ADDR then specifies the size and bytes of the address structure, sure. Traditionally this operation is called assigning a name to a socket. There you go. So that's what bind does. Okay, over here, when we call bind, so you notice we're using in-add or any right there. So our address is a little bit flexible here. It could either be localhost or it could be 74.118.22.75 or whatever's on the local machine. And this is a common way to write a server. The reason is for a server, I mean, you could go look up the machine's IP address and specify that address right there. That'd be fine, it'd work. But that'd be a little strange. It's better just to say, yeah, listen on whatever we listen on. So that's what in add or any is, special value for that. All right, so once we got our socket here, we can assign an address to it right there. This H tons, right up there. I've not mentioned H tons. All right. So these convert between host and network byte order. H tons right there, it takes a uint 16, an unsigned 16-bit integer. That's what the port is. You got 65,536 ports, and so it's an unsigned 16-bit integer. So you take that and convert it to network byte order. So you can go either way. This is a host to network short. This is a network to host short. All right, part of the point of using these functions, you notice it talks about host. It doesn't say this converts little endian to big endian. It says it converts host to network. All right, network byte order is big endian, but the host one can vary. If we took this little simple server and we went and compiled it on, say, a Sun workstation. Say we found one at a yard sale. I don't know what kind of yard sale we're at, but anyway, it came out of the basement, all dusty. Made in 1992. All right. If we compile this on there, this function is just going to go away and do nothing. It's already a network byte order. It's big endian on the machine, it's big endian on the network. And that's why the networks are big endian, because most of the machines on a network are big endian, right? I mean, how many times do you see a little endian machine hooked up to a network? Ridiculous. Well, it was in the 80s. Anyway, so this, networks were set up by the kind of the most common byte ordering in order to reduce the number of conversions. Well, you know, joke's on us. Nowadays, just about every machine on the network is a little endian. But that's where this came from. Anyway, so you use these instead of converting it manually or something like that. If you got a single byte, don't worry about it. If you have a protocol that uses little endian, and they're not super common, but you get to deal with one for this class, then you can just forget all about this stuff. I actually did the LRC protocol that we do little endian. As far as I know, nobody has ever compiled a LRC server on a big endian machine and probably never will. So I decided, oh, why not? It's a new protocol. We'll do things differently than everybody else. Okay, besides, that way you have to think about it, because you got like one that's different than the others. I actually have been, at first when I did the protocol for the server for this class, I kind of deliberately made it a bad protocol, so everybody at the end would be like, oh yeah, these are all awful ways to make a protocol. You really learned something from it. It was such a headache. I relented the next time. I tried to make it better designed. It's like, you know, this is not a good example. This is just too much pain. All right, there we go. So there's that socket, and okay. So socket, I didn't really explain them. I kind of started on binding, so I started with that structure. Anyway, this creates an endpoint for communication. And what it gives you back is actually a file descriptor. So this in here, it's not a status code or anything. It's a file descriptor. So remember on a Unix type system, let's, all right, read, we'll call it parrot. All right. So let's just void main it. All right. So we're going to go ahead and read from a file descriptor 0, and we'll go ahead and make a buffer. And it's just going to be 8 bytes. And we're going to read 8 into there, and then we're going to, let's just write. All right, then we'll write a new line. 1. Yeah, that's what I want. All right, there we go. There's a parrot program. I think I'm going to give it std2. That has the standard Unix functionality. All right, so here's what this should do. Let's see if it does do it. And that way, if it doesn't work, I can fix it first and then explain it once it works. Yeah, see it printed out high. Incidentally, it also printed out a new line. All right, so it consumed up to the L, then it left the rest of it and never even looked at it, and then the terminal tried to run it later. All right, let's go back to this program here. All right, so when we read from file descriptor 0 is standard input. That is the keyword. It doesn't have to be the keyboard. It's the keyboard because I didn't type anything into it. If I say something like echo golf ball, that's 8 letters, okay, into A.out. It comes back out the pipe. So we entered golf ball, it went into the program read it, the program printed it out, and it's right there. All right, that's standard input is 0. And then we go ahead and write our word back out to standard output. Well, standard output is 1, and standard error is 2. So if you have an error message, print it out on 2. All right, so that's the read and write functions. A lot of times you see people use printf, which is a library function, which is intended to make using these more convenient. But under the hood somewhere, it's calling write and sending stuff out to file descriptors. All right, over here in this network program, the simple server, socket, we're getting back a file descriptor that we can use read and write on. All right, so we got our file descriptor for socket, and then we're going to bind our socket, by file descriptor here, to our address, and then we call listen and start listening. All right. Oh, there's one thing I didn't answer on the socket. Which is protocol here at the end. So I just went ahead and set it to 0. And all right, so down here, see we got type first. And so here's an actual list of types. They keep mentioning, well, there's other ones out there. Now, most of these aren't that common. Kind of wish INET 6 was more common. But there's a fair list of ones that it supports. So if you want to make an Apple Talk socket, you know, go for it. All right, so then okay, so that's that's the domain, first one. All right, second one, type, and so socket has the indicated type, and so you got a few different types you can have. So we picked the sock stream that provides sequenced, reliable, two-way connection-based byte streams. There you go. We have a dgram. We can have datagrams, connectionless, generally considered to be unreliable, but yet it can actually be fairly useful for certain things. Most of the rest of these aren't ones that you very commonly use, but for example, if you want raw network protocol access, you may end up wanting sock raw. All right, and then finally, and then we got the options. We can have a non-blocking one, no, we won't go into that one very much. All right. So then finally, where's the last one? It doesn't tell me what I'm going to say. All right. The protocol specifies the particular protocol to be used with socket. All right. Normally, only a single protocol exists to support a particular type within a given protocol family. In that case, it can be 0. All right. So typically, it always is 0. If you're using an IPv4 socket, that's the type you have. There are multiple IP version 4 protocols to choose from, and so you just pick 0. So I think it's a little bit more of a, they put it in there to be flexible years and years ago. All right, listen. I mean, you are listening. All right. So okay, so listen, listens for connections. So servers typically sit around listening. And so it takes the connection there, but then we got this backlog one. And so the backlog defines the maximum length to which the queue of pending connections for SOC FD may grow. If a connection request arrives and the queue is full, the client may receive an error with an indication of connection refused, it might retry or whatever. All right, once we listen, we can go ahead and accept a connection. Once you've accepted a connection, it's not waiting for the connection anymore. And so that doesn't count as one of our 5. We can have 5 incoming connections we haven't accepted yet. So if you have a higher number, you'll be able to handle more incoming connections at once, assuming your loop to accept is taking a moment to accept them. So a higher number there will make you more resilient to somebody, for example, making 1,000 connections at once. Now, whether or not you want to be is another matter. If somebody is attempting a denial of service attack, it might be okay if your pending connections fill up and they get a whole bunch of connection refused errors. On the other hand, if you're under a denial of service attack and you want to stay up, then maybe you want a longer queue so that legitimate clients aren't forced out. Anyway, that's what that number indicates. How high can you set it? I don't know. Depends how good your hardware is, I guess. All right. So there we go. We're listening. So once we're listening, we're set in terms of we're now sitting there looking like a legitimate server. But in order to actually do our server behavior, we have to be able to accept an incoming connection. All right. This is one of the more easily mixed up bits of network programming. So we've got our socket here. It's a file descriptor. Should be able to read and write to it. But when a client connects, we're going to get a new file descriptor for that client. So what we're going to have is one file descriptor that indicates the socket we're listening on, and really the thing we're going to do with that is just use it for listen and accept and whatnot. And then we're going to have individual file descriptors for each client that connects to us, like a list of them. And we're probably going to have to keep track of these somewhere if we're dealing with more than one client at a time. Anyway, accept gives us back a client file descriptor. And so once we've got the client file descriptor, we can use it for stuff like writing too. And then we close it. All right. Now, accept has a couple parameters here I've set to 0. These parameters can be kind of useful. So let's go ahead and build a simple server, and I'll go ahead and run it, and we'll go ahead and connect to it. Notice I'm on Isoptera here, like Isoptera. So if I'm already on Isoptera, I can call it localhost and connect to 5100. All right. Get confused. Oh yeah, this is 5140. All right. Says good morning. Cool. Our server says nothing. All right. So let's go ahead and put at least some kind of note in here. All right. All right. So we'll say accept the connection there. We go ahead and rebuild this and connect to it. Oh. All right, let's try that once more here. We didn't bother to close anything, like we didn't close our socket. And since we didn't close it, it's still open from the last program, and so we can't reopen it. It would probably be a good idea to close it. That might actually take care of this. All right. Okay, but the last one's still open. So I'm just going to change to 5141 for now. Eventually the operating system will deal with it if you leave a socket open. It won't stay open forever, but it'll take a few minutes. All right. There we go. Good morning. Hey, it accepted a connection. Look at that. Oh, it's accepting a bunch of connections. Everybody wants to hear good morning. All right. Well, who's connecting to it? All right, so let's take a look at accept here. Let's put it right down, not that one. That one. All right, accept a connection on a socket. All right, so accept can take as parameters a sock address, like an address, and an address length. So what these are for is to let you know who just connected to your server. All right, so let's go ahead and do that. So what we'll get from accept is a sock adder in. We'll go ahead and make it. All right, that'll be our client. Let's say client ADDR for client address. Cool. All right, so down here I should be able to say the address of client ADDR. All right, this will be the size of it. All right. A couple notes here. This is expecting a pointer, an address, so we're going to take the address of our local structure. Should take care of that. The reason it needs an address, part of it is they don't want to copy the data. Addresses can be large, typically larger than a pointer on a system, although our system is actually 64-bit and our protocol is using 32-bit addresses. But we've also got the family and the port, so it's probably around 64 bits, I guess. Anyway, it leaves it in place. But on this one, it's actually going to change data here for us. Remember, in C, you can only return one value. And so if you needed to get something else back too, a convenient way is to send a memory address, and then you can just go ahead and change whatever's there. All right, there's the amount of memory we have for that client address. Since accept is working with a particular socket, it should know what the address family is. All right, so there we go. We got the address there. But then after that, it'd be nice if we knew who it was from. All right, so let's take a look at that address. It's going to be a little bit more complicated than maybe we think it should be. All right, so we've got the address right here. It's in our sock adder structure. But as you can see, it is a unsigned 32-bit integer. All right, why not? So the connection from %, that'll be a U, an unsigned. One line at that. And so we want client adder dot in adder dot s adder. Oh, it's in there, because there's a name right there. Keep reading it as sign. Anyway, so we've got there's the in one. It's a sock adder in is what it's for. So take the awk adder underscore out. There's why you have this sign prefix and everything. All right, so there we go. Let's see the rest. All right. Oh, it gives us a few little warnings here. All right. Passing argument number 2, except from incompatible pointer type. So these are just warnings, but we'll go ahead and make them go away anyway. So the way to deal with that is just like we did right up here in bind. You can see we cast this to a struct sock adder. Remember, it's except like bind expects a struct sock adder, not a sock adder underscore in. So that should take care of that first warning. All right, second warning. Size of, except makes a pointer from an integer without a cast. Expected a sock len. Oh, that's an actual mistake. All right. So if you look over here, it's a sock len t pointer. All right, we can deal with that. So the length, that's really long, whatever. All right, so we're going to give it the client address length. All right, as mentioned before, it knows which address family we're dealing with since we're passing a SKT. Well, it'll actually give us the length of the address that it's sending us. So this will tell us how long our address was that's in there, but we didn't really need to know that necessarily. All right. Argument 3, what do we got now? Expects a sock len t. All right, fine, we'll call it sock len t. I think this is not an actual error this time. All right, there we go, no errors. All right, accepted a connection from, that. All right, so let's not be on iSopra, and let's say netcat iSopra.16.edu, port 5141. Hey, look at that, different address. Want to connect here from the lab? Yeah, it is a different address. You can, the conversion here to an IP address and dotted notation is very straightforward. You just take it one byte at a time, and for each byte, you want a number 0 to 255, and you want to draw a dot between each byte. Not too hard. You write a program for that in, CS-111. There's a library function for it, though. All right. 7's right. All right. I'll go ahead and disappear that for a minute. Okay. What's it called? All right. So we got. I mentioned C. We can go see also all of this other stuff, capabilities, etc. I'm actually drawing a blank on the name. It's like, well, still don't remember. All right. There's a library function that does basically exactly what I said. It goes through one byte at a time, makes you the address in dotted notation. I probably have it in my examples. I'll go grab it. I know where it is. I can find it here. All right. So I find the rules 2.0 server. Oh. There. All right, so somewhere, it's down near the bottom, there's an accept, so bind, we listen. When we accept, wait a minute, we don't track where our connections from? Well, that doesn't help us. All right. Oh, maybe the lab one server does it.
INET underscore NTOA.
Yeah, or
Or is it?
No, that's
ATOA?
yeah, that's you're right. That's the right family. You want to search the family, it's fine. Yeah, good searching.
I
All
tried
right.
to remember too. I was like, I've used this in the past.
Yeah, you're yeah, good job. All right, so it's this one here, yeah, NGA right there. So INET end A returns a char star, that is string, that's what we wanted, something we can print out, and it takes a struct in adder in, and yeah, so let's go ahead and use it. All right. Here's all right. So it converts the internet host address IN given in network byte order, so you don't even have to change it, to a string in IPv4 dotted decimal notation. All right. So a string. Now here's one caveat on this stuff. Notice it returns a char star. If you're returning a memory address, the memory address must go somewhere. So there's two scenarios that are common. Number one, it leads to something dynamically allocated that we have just taken on responsibility for freeing. That's not this one. Number two, it leads to a buffer somewhere. In this case, it's a statically allocated buffer, which subsequent calls will overwrite. This is not thread safe. Because if we were to call it 2 times from different threads, one would be overwriting the other. All right. There we go. And hey, there's what an in adder is supposed to look like. Cool. All right, back to our little program over here. It's instead of %IU, we want to print out a string. And instead of this, we want to say INET N2A. And I think we just go to there. Let's see, in adder struct. All right, let's see what happens. All right, implicit declaration of that one. So evidently we didn't include. There's a number of includes up here for these things. We got socket already. We probably have net inet in.h. We're probably missing our inet.h. All right, that should probably take care of it.
It's
Don't mind that, yeah.
Yeah. All right. There we go. So now we go ahead and connect to that thing. We should see some. Oh, there we go. All right. So 192, 118, 222, 224 would be the campus Wi-Fi. The gateway for the whole campus is there. And then that was me here at this system, and in front of me, the 192, 168, 1825. And actually, from the fact that iSoftware knows that, we could probably figure that iSoftware can actually connect back to us. And then 127.0.0.1, that's the local host adapter, so that's somebody that is logged into iSoftware. All right, cool. We can connect to these things. Oh, there's somebody else from the campus Wi-Fi. Yeah. All right. So there's the simple server there that says, good morning. All right. Okay, what's next? All right, what if we want to send things back and forth? Well, we'll go to a client and we can see that. All right, so for the client, we have to deal with addresses more as a client. You may be tired of addresses, but too bad. All right. I have a second client up there, and let's go take a look. All right. So here is a client. A lot of the stuff is a little bit of a duplicate of what we've done before. The client has, with the server, it's a little irritating. You have to go change the source code to switch which port the server listens on. With a client, it's very irritating if you have to change the source code to change which port you connect to. Maybe if it was a web browser, it'd be okay. Sometimes. Like the web browser you can't use to configure routers and stuff. All right. So the client, I went ahead and just took the arguments here. The other thing that would be irritating if you can't specify in the client is what you want to connect to, like the address of what you want to connect to. I expect to be able to say, this is the address, this is the port, let's go ahead and connect now. All right, so this one is actually using args and argv up here. This is often called argc. Argc is probably more common than args. You do see both names if you look through examples. We're going to do our conversion here on, this takes A to I here. So you notice that the address there, we said like N to A. And for the INET, we convert it to A. A represents text a lot of times in the names of these functions. And so in this case, we're taking A, that is text, converting it to I, that's an integer. And so once we've got our integer, we can go ahead and convert it to the right port. I think A to I actually returns a 32-bit signed integer. It doesn't cause a practical problem here. A 32-bit signed integer actually has a larger range, and for the first 2 bytes, it's going to be the same. And so it's not an actual problem, but there is a little bit of a mismatch there. A to 95 would refuse to compile it. All right. That's our port, our address family, same thing. Socket, make that the exact same way, not a difference there at all. All right, so then this whole circus right here. All right. So the reason for all this stuff right here has to do with the fact that we might not remember the IP address we want to connect to. It's nice if you can specify something expecting the DNS system to take care of it for you. All right, so I got this struct hostin and this get host by name. All right, here's get host by name. There's a whole family of these things that do things slightly differently. Looks like get host by name is first. All right, so get host by name function returns a structure of type host int. You saw that, we'll look through a little bit later, for the given host name. So here host name is either a host name, that is something we can look up, or an IPv4 address in standard dot notation. So you can actually pass it either, which is very convenient in a user interface perspective to be able to specify either one. If you used a web browser, you might expect that. All right, or an SSH client or whatever. Okay, so if it's an IPv4 address, no lookup is performed, and get host by name simply copies name into the hname field and instruct inaddr equivalent into the haddr list 0 field, the return host int structure. All right, so a host int structure is what we expect to have come back from a DNS query. And so basically what it's doing is it's skipping the whole query and making us something that looks like a DNS query result, but actually just specifies the IP address we said. The reason is to get us a common point here, because a lot of times in these programs, you run get host by name first, and you expect it to give you a DNS entry. You don't really expect the user to enter an IP address, but if they do, it's nice if it just makes up something that looks the same and works. All right, if name doesn't end in a dot, all right. Anyway, does a DNS lookup. All right, so it returns this host int structure. And so that's what a lot of the rest of this stuff is for. All right, so DNS lookup what the user said, and we get this host int entry. We actually get a pointer to a host int. So you can see from this little pointer thing here, we never free this host int. It just gives us back a pointer we can use. So there's going to be a statically allocated buffer somewhere, and so we're probably looking at a thread safety issue here too. All right, host ints. All right. So you can see that's a pretty common currency in these functions relating to DNS and getting hosts by addresses. There's a number of different variants on the get host ones, anyway, host int structure. All right. So the host int structure is defined in netdb.h as follows. Okay, so first we got an h name. That's the official name of the host. I don't know what gets copied into there if you just enter an IP address, probably just the IP address. Then you got a list of aliases for that host, other stuff it's called. You've got an address type and an address length, and then you've got a list of addresses. Well, sometimes when you do a DNS query, you actually get back multiple addresses, depending on what you're querying. A lot of times large websites are distributed over a fair number of web servers. You know, Google isn't just running on, you know, a desktop sitting somewhere. So if you've got a lot of those, first of all, the DNS query may resolve differently depending on where you are geographically. And secondly, it may give you back a list of addresses that all actually are valid addresses for whatever DNS entry you've looked up. All right, so you might be able to get back a whole list here. Okay, and then there's this pound define haddr. Haddr means haddr list entry 0, like the first one in the list. A lot of times if you're programming these and you're like, well, I don't really care if there's a list or not, I'm just going to use the first thing that resolves to it regardless. You know, that generally speaking will work. Because if there's a number of IP addresses behind some particular entry here, generally speaking, they're all serving up the same thing and it doesn't really matter which one you use. That said, in a load balancing sense, it might not be ideal if everybody just picks the first one. But with the load balancing, that's why in some cases geographically it'll give you a different one. It's giving you something that's close to you, so that you're not using like Google's server in Mongolia from here. All right. There we go. All right. So over here, if you take a look at this. This is an incantation that I rarely get right the very first time. We want to get back an in adder. We've been looking at these in adders before, and of course you can see up here on our address that we're connecting to, we've got port, family, and what we need is the in adder. So that's what we're looking for right there. And so if we take this address list, I did a couple of casts here to try to show this a little bit more step by step instead of putting it all into one line. But you can get it into one line if you work hard enough on it. You just got to get a few more stars and parentheses in the right spots. It'll work. All right. We're going to take the haddr list and just put it in its own variable here. And we're going to take entry 0. Notice there was that pound define there we could have used. And that's going to give us our address, our caddr, our address that we're going to connect to. Looking at that, I thought client adder this time, but when I wrote that, I thought connection, like the thing we're connecting to, is address. All right, anyway, that's where we're going to connect. Now, this IP string right here, this is not essential. You could leave this line off, but you do have to leave this line off if you also do it. I just wanted my client to say what IP address we're actually connecting to, like where this resolved to. We're setting our address here to the address up there. All right, so once we've got the address set right here, and we know what we're connecting to, then we can call connect. And from there on, you can see the client is actually much simpler. The DNS query part is most of the complexity in the client for stuff like this. If you're writing a client that actually does something, you know, it might be like, okay, we finished that part. We're done with all the complicated part. Now let's set up a GUI. All right, so connect. Connect, I'm not even going to look at the command page. You take your socket and you're going to connect it to the thing at this address. And this is the size of the address over here. Same kind of parameters we're looking at for bind or accept. All right, so I can go ahead and write something to it. In this case, we're writing hello. We're writing 6 characters. We'll go ahead and do the null terminator that's at the end of the hello. We don't necessarily have to send the null terminator across, but in this case, we're doing it. And then we're going to close our connection. All right. All right, I'm going to actually name this thing this time. We'll call it SC for simple client. All right. Let's split the screen here. So, if I, so since I can connect back here anyway, netcat, listen, port, I'll pick 2000 today. All right. So then I should be able to say up here, run SC, and we'll connect to 192.168.18.25 on port 2000. All right. So up there, you see it's connecting to, well, I mean, you know, pretty obvious there. the thing that was at that address. And so down here on netcat, we got hello. All right, let's reverse this operator. Well, let's do this. We'll connect to it. We'll go ahead and connect to a software here. All right. So I'll go ahead and run netcat and I'll listen on port 2000. And up here, instead of this one, we'll just connect to localhost. All right. So we ran through the whole DNS thing here. We set localhost. So get host by name received that text, localhost. So then localhost, instead of it doesn't have a DNS query, and you know, an IP address in dotted notation, it'll do a DNS lookup. My guess is it's got a special line in there. If it's localhost, don't bother. Yeah, if it did, the DNS server was like, localhost resolves to 127.0.0.1. Anyway, but my guess is it didn't actually look it up. But what it did do is put an actual IP address in for localhost. That is 127.0.0.1, and so that's what we looked up there. All right, let's do it again. All right, this time, instead of that, we're going to say software.lcc.edu. All right, now we're connecting to 74.118.22.194. I occasionally say a different number. My software used to be somewhere else. Anyway, so that's the IP address for the outside on my software. All right, so that's a simple client. As you can see, not too much to it. And now we've both read stuff from sockets and wrote stuff into sockets. So you've seen both of those. All right, see, it's somewhat complicated, not in Python. If you look this stuff up in Python, you'll find it very much shorter. Okay, so I was thinking about using these and making a remote mass server, but we'll probably end up doing that next time. Now, there's, how do I put this there? Lab 1 client. Should be in there. It's there, good. All right, so when you're on Lab 1 client, which should make all kinds of sense now, Lab 1 client will connect to a particular port and send out a message. And so you got to figure out the message that it sends. So for this one, you'll want to have a netcat listen somewhere. So you start listening somewhere, then connect to it with that client, and you'll see what message it sends. So basically, this lab has to use netcat for both parts of the interaction. It shouldn't really take you very long, but it's kind of an important skill because when you're writing network software, a lot of times you're like, okay, I just need a simple, reliable program that will let me see what my server says. Netcat can be that for you. If you have a binary server, you can use netcat if you want to, but it won't print it out in any nice form. One thing you can do if you're like, okay, when I connect to my server, it's saying something. I don't know what it's saying. You can go ahead and take netcat, redirect it into a file. And then you've got a file that contains whatever your server sends out. So then you can look at your file and examine it and figure out what's in it and see if it's appropriate or not for what the server is supposed to say. That's one way to do it. The other way to do it is with Wireshark. And, all right, there's 100 other ways to do it too. One other way you can do it is with Wireshark. Okay, let me open up Wireshark real quick. Let me close the web browser real quick because they tend to send persistent traffic that fills up Wireshark with stuff. All right. So we got Wireshark on here. We're going to go ahead and start capturing, except we don't have permission to capture. If I sudo Wireshark, am I going to have a problem? Okay. All right. Finally, hey, it looks like we're good. All right. So we're capturing. Now you notice there's an awful lot of just like network traffic, queries, stuff. Yeah, that happens. You can see, let me go ahead and make this bigger real quick. I wish I could make the interface bigger, but I can't even read that stuff. I haven't done the projector, I can do it here. So what we're seeing is just kind of extraneous network traffic. Mostly these are just queries for this, that, or the other thing, name queries, that kind of stuff. So what I wanted to do with netcat, though, see this is increasing very quickly, is go ahead and capture something that we actually sent on. So let's do our best here. All right, so on software here, I'm going to go ahead and run simple server. That's actually compiled as a.out. All right, so that's running on there. Now on here, we're going to go ahead and say netcat software.lcsc.edu port 5141. All right, I'm going to hit stop as soon as I send that. All right. So now that I probably just captured that packet here. So, where's the end? There's the end. All right. So we got protocols here, and this is going to be a, I'm not sure what protocol it's going to tag it with because it wasn't really following any in particular. It may be this TCP interaction with that software right here. So in the text that you can't read, the source says 192.168.18.25, the destination says 74.118.22.184, which is our software. And so we've got some TCP traffic. And at the end, we've got this thing called an encrypted, oh, that's SSH, sorry. So the TCP, here, this is the contents of what was sent across. And I don't see good morning in that one. TCP is a kind of a complicated interaction here, but this is the one that actually involves our message we sent. If we look down here at the actual contents of what went across, this is related to TCP. We'll talk about TCP when we talk about layer 4 in like 2 months. But at the end here, you can see our text. Good morning. The gap there is not like a new line or a space. It separates it here. We put it into 64-bit chunks on each side, just as an organizational thing. Yeah, there's good morning went across the network. So if you wanted to say, what is my server sending? If we look up here, in this text you can't read, it says data 13 bytes down at the bottom. And if we click on that, it will highlight the actual data, like ignoring TCP headers and IP headers and all the other stuff that's part of this packet. The actual data that we sent starts right there with that G. It's highlighted for us. Now you definitely can't read it. It says good morning. All right, so Wireshark will let you see what went across the network. So if your question is, what did my server just send? Yeah. It's got a wide variety of filters. I just went and caught it and scrolled up to it this time. But if you're really interested in finding your packet with Wireshark, figure out how to use the filters. They're very elaborate. They solve all kinds of problems. They're not necessarily intended for somebody to walk up and use the filters with no study whatsoever. So, you know, sit down when you got a few minutes, figure out how to use them. They were pretty good. All right.